So now I'd like to introduce Alexandra Baumgart, who's studying mechanical engineering at Caltech and did her practicum at Los Alamos National Laboratory, and she will be presenting on reduced order chemistry modeling for detonations.
All right, thank you for the introduction, and thank you all for being here. So today I'll be talking about part of my thesis work at Caltech on chemistry modeling for detonations. So why do we want to simulate detonations in the first place? There's a variety of application spaces where this is relevant. First, safety is a big aspect of this. So throughout history, there's been many instances of accidental explosions with nuclear or chemical plants, coal mines. And so being able to predict these events to hopefully prevent these catastrophes is an important aspect. And one means by which these accidental explosions occur is through what's called a deflagration to detonation transition, where something starts out as a fire, and eventually that flame accelerates into a detonation, becoming much more destructive. Another area is in propulsion. So the energy generation in detonations can be much more efficient than in standard gas turbine engines, for example. And there's been work experimentally and numerically on developing rotating detonation engines, such as the one pictured here, to really leverage that energy generation. And there's also examples in astrophysics as well, since I know there's some astrophysicists here. So detonations are relevant to a lot of areas, and there's also a lot of modeling challenges involved with detonations. So first, I just want to go over what exactly is a detonation, what's the structure of it. At a very basic level, you have a shock wave that's followed by chemical reactions. And so if we look at a 1D model of this, I'll be referring to the ZND model, which is just a 1D detonation model. So we have temperature on the left axis, pressure on the right axis. First, you have a shock, followed by a region called the induction zone, where temperature, pressure are constant. And then this is followed by a reaction zone, where chemistry is occurring, our thermodynamic variables start to change. If we look at kind of in the composition space, or in the composition what's happening, I'll be talking about hydrogen combustion. So our reactants here on the left, we have hydrogen and oxygen. Through the shock and through the induction zone, they remain constant. Relatively constant. And then in our reaction zone, that's where we start to have a lot of changes in the chemical composition. We form water, our reactants are used up. If we go to multiple dimensions, the structure becomes a lot more complicated. We can no longer assume it's a steady detonation. There's a lot of unsteady processes occurring. And what I'm showing here is the magnitude of the density gradient. So where there's darker lines, those are shock waves. And the red line is indicating kind of where the chemistry is starting to occur. And there's a few key features I can point out here. Where the shock and chemistry are occurring close together, we have what's called a Mach stem, so it's propagating faster locally. Where we have more distance between the shocks and reactions, the detonation is propagating slower. That's our incident shock. We also have shock waves that are moving up and down along the detonation front, and these are transverse waves. Where those three waves intersect, those are called triple point collisions. And again, this induction zone length, the distance between the shocks and the chemistry, is now varying along the detonation front before we get to the reaction zone. And so I just want to go over an example of a detailed chemistry calculation typical for what we would be looking at. So this is a hydrogen detonation. We're diluting it with argon. And I'll go over what I mean by detailed chemistry on the next slide. So we start with our 1D detonation model. I'm showing the pressure, density, and temperature profiles for what that looks like. And then to do a 2D calculation, we take our 1D solution, perturb it onto a 2D grid, just with some sine waves, essentially. And so here I'm again showing the density gradient. We have our unburnt reactants on the left, our burnt products on the right. And I just want to note that for these simulations, NERSC and/or Access computing resources were used for these calculations. So if we let this play, initially you can see there's some instabilities that move away from that initial perturbation. And over time, we start to see kind of these regular patterns emerge with the transverse waves moving up and down. You see some shock collisions roughly evenly spaced along the detonation front. So it's a very complicated, multi-dimensional structure. And so now I'm going to go over kind of typical chemistry models that are used in detonations. So apologies to the computational chemists. This is much simpler than what your chemistry modeling is. But so the simplest approach we can have is one-step chemistry, where we have a single global reaction, and we only need to keep track of one chemical species. So for example, how much hydrogen we have, that's our fuel. So you don't need to keep track of anything else, which is very computationally efficient, but it oversimplifies a lot of the physics. On the other extreme, we have detailed chemistry, which was what is used for the simulation on the previous slide. And here we have a lot more information. We keep track of our reactant species, our product species, and all the intermediate species in between. So you can see we have 9 species here, depending on the diluent that we're using. And in order to track all of these, we need all of these reactions, each of which have their own reaction rates. The list of equations is not important here. It's more just the quantity of what we need to keep track of in our simulations. And so as you might imagine, this drives up the computational cost significantly, which is not good if you want to simulate, for example, a large-scale engine and you want to actually have all the information. So another approach, this table is just summarizing kind of the number of scalars and reactions that we need to keep track of depending on the chemistry model. But another approach that's been commonly used for flames, so not detonations, is what's called the tabulated chemistry approach, where we have a progress variable C transported according to this PDE. And what this progress variable does is it tracks the progress of your reactions from the unburnt reactants to the burnt products. And this progress variable is then used for a table lookup to get all of the other quantities you need from your simulation that normally you would be getting from your detailed chemistry. And so by doing this, we have more information than a simple one-step chemistry model, but it's still at that low cost because you only have one scalar that you need to transport in your simulation. And so here's just an example of what that progress variable could look like for a detonation. And so the goal here is to extend this tabulated chemistry approach for detonations. And so I just want to give a few details relevant to our CFD code, skipping over a lot of numerical details. But essentially, in the code, we transport the mass, momentum, and energy. And so that's just with the Navier-Stokes equations, if you're familiar with fluid mechanics. And then to get the temperature, we have this inversion where we use our transported energy to extract the temperature at a given time step. And then we close our system of equations with the equation of state to get the pressure. So there's a couple of things we can notice from this solution procedure. In terms of the thermodynamics, we see for that temperature inversion, where I've bolded some of the variables, we need the mixture enthalpy, H, as well as the specific heat capacity, Cp, in order to get that temperature. And we have those quantities naturally through the NASA polynomials as a function of temperature. And so that leads us to use the temperature as one of our table lookup coordinates. And then on the chemistry composition side, we know that we need to have a description of the mixture, possibly through our mean molecular weight W. And that's traditionally, this is well parameterized by the progress variable, which we're defining here as the mass fraction of water plus one of the initial radicals in hydrogen combustion. And so that gives us our second table coordinate, the progress variable, to close the system of equations. To generate the table, we're going back to our one-dimensional detonation model, because those are cheap calculations to do. And so if we take a variety of detonations, one-dimensional, propagating at different speeds, we can, each of these black lines is a different detonation solution. I'm showing this in our temperature progress variable space. And so once we have those solutions, we can fill in our CT space for the quantities that we need in our table to be able to run the simulations. So for example, our enthalpy, our molecular weight, and the source term for the progress variable, which is the source term is what I'm showing here in CT space. So with this, then we have everything we need to be able to run with the chemistry table in our simulations. And so here are a couple of videos from a tabulated chemistry simulation. The density gradient is on the left, the progress variable is on the right. And so we see there's a lot of complicated flow features here, lots of shock collisions, some vortical structures in the wake. And so even with this very simplified chemistry model, we see that the general fluid mechanics involved were able to reproduce that. And we can also look at what are called soot foils. So this is the numerical version of an experimental technique that's used to track where those shock collisions along the front move over time. So they kind of etch out these diamond-shaped patterns that you see. And that kind of shows you the time history of what the detonation wave is doing. And so I'm showing the detailed chemistry simulation results on the left, tabulated on the right. And we see that we're able to produce very similar looking structures between the two. And depending on the mixture composition for the detonation, we see different types of structures, different sizes, different shapes. But the key is that we're able to get it with our simplified chemistry model, reproducing the results from the more expensive simulation. So in terms of the computational cost, overall, for hydrogen combustion, we had over a 4 times speed up in our simulations. And I'm showing here the CPU time per point for different components of the code. There's a couple notable differences. First, with the scalar transport, we go from having 9 species that we need to transport down to 1 scalar, the progress variable. And so we see about over a 9 times speed up in the cost of that part of the simulations. The other area we see a big decrease is in combustion, which is where we compute all of the chemical source terms for all of the reactions in the detailed mechanism. Whereas when we do the tabulated chemistry simulation, we reduce that to a simple table lookup. So it's much cheaper, over 17 times speed up there. And I want to note that for hydrogen, this is the simplest fuel you could have. If you move to hydrocarbon fuels, those detailed chemistry calculations are much more costly. And so we would expect to see an even greater benefit there if we use this approach for larger chemical mechanisms. And so just to conclude, by generating a chemistry table in CT coordinates, we had promising results for a variety of detonation cases, not all of which I was able to show today. And we had a significant computational cost savings for hydrogen fuel. And so with that, I'd like to acknowledge my group at Caltech, as well as the CSGF for support throughout my PhD. So thank you, and I can take any questions.